It wasn't long after rotary rigs first came into widespread use that drillers developed the maxim, there's no such thing as a straight hole. Wells that were supposed to be vertical often drifted off course, missing pay zones, crossing lease boundaries, or even intersecting other wells. They exhibited abrupt hole angle changes known as doglegs. These resulted in pipe failures and, in extreme cases, made it impossible to run casing or completion equipment. Crooked hole tendencies were seen early on as a drawback to the use of rotary tools, but the inherent benefits of rotary drilling ensured that it was here to stay, and so the industry concentrated on finding ways to minimize these tendencies. Over the years, we've been largely successful at learning to control wellbore deviation. Moreover, we've developed ways to actually guide drill bits to specific targets, a practice known as controlled directional drilling. Continuing technical advances have made possible new levels of directional control, and applications that were once the stuff of dreams have become almost routine.
In this video library module, we'll consider some of the technologies and applications of directional drilling. We'll discuss what's involved in planning directional and horizontal wells and see how we go about drilling them. We'll also talk about the fundamental differences between directional and vertical wells as they relate to developing a drilling program. Directional drilling is a way of reaching otherwise inaccessible targets. This makes it a valuable, even essential, reservoir management tool.
Inaccessible targets might include offshore reservoirs, where we drill multiple wells from artificial structures, onshore reservoirs underlying urban developments, mountainous areas, or other surface obstacles, reservoirs underlying salt domes, which could cause innumerable drilling problems, and reservoirs associated with faults, where drilling vertically through steeply inclined fault planes could result in sheared casing if slippage occurs. Where drilling characteristics are well known, we can use directional drilling to take advantage of a bit's natural walking tendencies by offsetting the surface location and letting the bit drift to the target. We can use directional methods to sidetrack, straighten, re-drill, or re-enter an existing well. Relief well drilling is an invaluable tool in well control. When surface control methods can't be used to stop a blowout, an alternative is to drill directionally and then pump kill fluids into the blowout well's annulus. Reaching otherwise inaccessible targets, sidetracking, re-drilling, relief well drilling. These and other applications have played a vital role in shaping the petroleum industry. Offshore development, as we know it, for instance, wouldn't exist if not for directional drilling. As technology has continued to advance, we've seen other areas of application assume similar importance. For example, horizontal drilling, the practice of directing a whole section laterally through the pay zone, is an old concept that came of age during the 1980s. In the right types of reservoirs, horizontal wells are a proven means of increasing formation exposure, raising well deliverability, and reducing development costs. Other techniques, such as drilling multiple drain holes from a single vertical wellbore, have likewise grown out of old ideas made practical by new developments. These developments have occurred in areas ranging from well planning to drilling tools to real-time surveying and logging capabilities. Before we consider some of these areas, let's look at some basics of directional planning. We can trace the development of directional drilling to the industry's long-standing concern with deviation control. Wellbore deviation results from forces acting on the drill bit. While the relationships among these forces are complex and not completely understood, we can say that they're related to formation characteristics, hole angle, bit type, bit weight, rotary speed, and drill string mechanics. The most significant research that's been done on wellbore deviation has been in the area of drill string mechanics. The extent to which deviation occurs is based on the drill string's buckling tendencies, which in effect dictate bit trajectory. For a given depth, hole geometry, and weight on bit, the degree of drill string buckling depends on the stiffness of the bottom hole assembly. By using stabilizers and large diameter drill collars at locations of maximum deflection in the predicted buckling mode, we can control the bit's lateral movement. The use of steerable or navigation drilling systems, which allow the driller to monitor and control bit trajectory from the surface, can largely negate natural hole deviation tendencies. Even so, proper design of the bottom hole assembly remains essential, and there are still numerous situations, shallow drilling at isolated land locations, for instance, where non-directional methods remain the most economical method of deviation control.
Directional and non-directional wells have similar planning and equipment requirements, although, as we would expect, directional well planning involves additional considerations. The most basic of these is establishing a well trajectory or profile.
Our goal in planning a well profile is to determine the most economic path from the surface to the bottom hole location. We first have to determine the target coordinates with respect to the proposed surface location. At the same time, we have to assign the target radius based on our well objectives. This target radius indicates how tightly we have to control the well trajectory. The degree of control is much less critical for a relatively thick, homogeneous interval than it would be for a thin, steeply dipping zone. Dogleg severity limits are based on drill string operating specs, completion considerations, and other factors. Note that it's possible to run into problems even when the departure from vertical is within an acceptable range. Here, even though the inclination is within its assigned limit of 3 degrees per 100 feet, the dogleg severity is too high. This illustrates the importance of measuring both inclination and direction, even on vertical wells. In laying out the well trajectory, we may start by looking at 4 general patterns: the build and hold, or Type 1 pattern, the build, hold, and drop, S-curve, or Type 2 pattern, the continuous build, or Type 3 pattern, and the build, hold, and build, or Type 4 pattern. The build and hold pattern employs a shallow initial deflection from vertical and a straight angle approach to the target. It's good mainly for reaching single targets at moderate depths, and sometimes for drilling deeper wells with large horizontal departures. The build, hold, and drop pattern likewise employs a relatively shallow deflection and holds angle until it reaches most of the desired lateral displacement. But then the angle is reduced or brought back to vertical to reach the target. This pattern is primarily for wells in multiple pay zones or where there are lease or target constraints. The continuous build pattern has a relatively deep initial deflection, at which point hole angle is maintained to the target. This pattern is appropriate for salt dome drilling, fault drilling, sidetracks, or redrills. The build, hold, and build pattern describes horizontal wells, of which there are several types. Selection of this pattern is based primarily on reservoir engineering considerations. We can define well profiles in terms of several key parameters. The inclination angle is the deflection from vertical at a given point, while the kickoff point is the depth at which we first begin building the inclination angle. The azimuth refers to the angle in the horizontal plane with respect to true north. The turnoff point is the depth at which we change azimuth. The turn rate angle represents the incremental change in azimuth over a measured course length, while the build rate angle refers to the incremental increase in inclination. Conversely, the drop rate angle on a build, hold, and drop pattern is the incremental decrease in hole inclination. The lead angle, measured in the horizontal plane from the left of the target area, accounts for the tendency of a rotary bit to walk to the right. Its value depends on local drilling conditions. Your manual contains some of the basic equations for calculating well trajectories. But remember that there's a lot more to planning a well profile than drawing a curve from point A to point B. Many other factors, well spacing, casing and completion requirements, rig capacity, hydraulics, drill string design and specifications, drilling parameters, and so forth, come into play. There are a number of software packages that can be used to optimize well trajectories while accounting for these drilling variables.
Of course, it's one thing to plan a well profile and another to actually attain it. And this is an area that has seen dramatic changes in recent years. In the next unit, we'll look at some of the tools and procedures used in modern directional drilling. For now, read section 1 of your manual and work the accompanying exercises. Attaining the initial deflection is a crucial step in any directional drilling program. Over the years, the industry has used a variety of deflection tools: whipstocks, directional wedges, jetting bits, and so on, with varying degrees of success. By far the most successful and widely used deflection tools are downhole motors.
Downhole motors are commonly known as mud motors because they're driven by the circulation of the drilling mud. There are two basic types of mud motors: positive displacement motors and turbine motors. The positive displacement motor, or PDM, is easily the most versatile tool for building or maintaining hole angle. It enables us to initiate deflection simply by incorporating a bent housing into the motor or by using a bent sub or eccentric stabilizer. The bent housing shown here is adjustable, thus providing even greater flexibility and directional control. Conversely, to keep a straight well course in crooked hole formations, we can run the motor without a bent housing or bent sub. The heart of the positive displacement motor is the rotor-stator assembly, where circulating fluid imparts torque to the rotor and causes it to turn. A universal connection transfers this rotation through a bearing and drive shaft assembly to a rotating bit sub, which turns the bit. The drill string itself does not rotate. This allows us to orient the bit in the desired direction. Positive displacement motors provide excellent steerability for deflecting or straightening the well course. In addition, they allow us to increase the bit RPM without increasing the drill string rotation and to drill with less weight on bit. This can result in higher penetration rates compared to drilling with a rotating Kelly and reduced drill pipe and casing wear, an important consideration, especially when drilling high-angle holes. Positive displacement motors are available in a wide variety of sizes, rotating speeds, and output characteristics for a broad range of downhole conditions. For more detailed information, refer to the references listed in your manual. A turbine motor consists of multiple rotor-stator assemblies that drive main thrust-bearing sections. These tend to have narrower operating ranges than positive displacement motors, and unlike PDMs, they can't accommodate bent housings. Still, they've seen wide use in the former Soviet Union, where they've undergone their most extensive development, as well as in other parts of Europe and in the North Sea. Although the mud motor is overwhelmingly the tool of choice for controlled directional drilling, there are other ways of initiating deflection that may be applicable in certain areas. In very soft formations, for example, jetting bits can prove effective. These bits have orienting nozzles which use hydraulic energy to gouge out a small pocket in the formation, after which the driller can drill a small pilot hole, run a directional survey, and reorient the bit if needed. In developed fields where drilling tendencies and formation characteristics are well known, we can use the drill collars, stabilizers, reamers, and other components of the bottom hole assembly to control hole angle, sometimes without having to use deflection tools. Bottom hole assembly design must take into account a number of factors and can become quite involved, but for the most part, the design will be a variation on one of two basic configurations. The pendulum assembly employs a stabilizer up above the bit to center the drill collars and prop them away from the hole. This increases the straightening force and acts to reduce hole angle. The packed hole assembly, shown here in several variations, consists of large diameter drill collars, which impart stiffness, and multiple stabilizers, which guide the bit straight ahead. When properly designed for the formation, it can be quite effective at maintaining a constant hole angle. Keep in mind, though, that stabilizers, especially large diameter ones, add torque to the drill string. They may also reduce the available weight on bit and accelerate hole erosion. And the smaller annular clearance that is characteristic of a packed hole assembly can greatly reduce the chances of a successful fishing job, should one become necessary.
To measure and control well trajectory, we have to be able to determine the inclination, azimuth, and tool face orientation at given depth. The scope, objectives, and procedures involved in downhole surveying have evolved and expanded dramatically over the years.
The oldest and simplest type of survey tool is the mechanical drift indicator, which works on a plumb bob or pendulum principle. It measures inclination from vertical, but not direction, and is used today mostly for surface hole drilling or for shallow vertical wells. For many years, magnetic and gyroscopic instruments were standard tools for measuring hole inclination and azimuth. These self-contained tools combine the pendulum drift reading with a compass measurement. They have three main components: a compass and angle indicating unit, a camera which records the measurements on a photographic disc, and a timer or motion sensor which activates the camera at a given interval. Tools are available with either single-shot or multi-shot capabilities. That is, some record measurements at one point, while others take a number of surveys along the well course.
Under the right conditions, and with the necessary corrections, Both magnetic and gyroscopic compasses can provide accurate survey readings. As discussed in your manual, each type of instrument has specific areas of application, along with certain limitations and requirements concerning accessory equipment and running procedures. Your manual also summarizes important advances that have enhanced the capabilities, efficiency, and accuracy of magnetic and gyroscopic survey tools.
Traditional survey methods have two inherent shortcomings, one being that we have to stop drilling while we run the survey. This can add up to significant expense, especially when rig costs are high and we're on a relatively deep well. The other shortcoming is that by the time we run the survey, the whole section has already been drilled, which necessarily lessens our control over the well trajectory. In such cases, and when we're drilling with a mud motor that has a bent sub or housing, wireline steering tools may be a good alternative. A wireline steering system consists of a bottom hole assembly that accommodates a measurement probe run on wireline. The probe has magnetometers that measure direction and accelerometers that measure hole angle. It also measures the orientation of the tool face and other parameters such as time, depth, and tool temperature. The wireline is either run inside the drill pipe or passed through a side entry sub and is connected to a surface computer which processes the information and provides a remote readout. The operator can then correct the tool face angle as necessary to maintain the well on course.
Two of the most important advances in modern petroleum technology are the development of real-time measurement while drilling systems to transmit drilling and directional information, and logging while drilling systems to provide formation evaluation data.
MWD and LWD systems have fulfilled a long-time dream among industry professionals by making it possible to monitor and control operations even as drilling is taking place. Examples of what we can now do continuously and in real time include measuring drill bit position and trajectory, monitoring penetration rate, actual weight on bit, downhole torque and drag, vibration and other drilling parameters, computing pore pressures and getting an early warning of potential overpressured zones, detecting and correlating geologic markers and formation tops, and evaluating formations even as they're being drilled. These systems are modular and can be run with various sensor combinations according to the well plan requirements. MWD tools operate by creating pressure pulses in the mud column in response to inputs from the various sensors. Depending on the type of tool, the pulses may be positive, negative, or continuous. These pulses are converted into electronic signals which are processed and displayed at the surface. The basic components of the MWD instrument package shown here include a battery-powered pulsar module, which in this case employs a continuous mud wave transmission, a sensor module containing triaxial inclinometers to measure drift and triaxial magnetometers to measure azimuth, along with temperature and pressure sensors, and an electronics module. This particular tool, together with its accessory modules containing the batteries and centralizer, is run inside standard non-magnetic drill collars. Logging while drilling, or LWD tools, operate on basically the same principles as conventional wireline logging tools. The dual resistivity device shown here contains a gamma ray tool and two sets of transmitters and receivers to provide shallow and deep resistivity readings. This compensated density neutron tool measures density and neutron porosity in a manner similar to that of analogous wireline tools. When drilling with a mud motor, these particular tools are run above the motor assembly, in other words, about 30 or 40 feet above the bit. In some applications, such as drilling in very thin dipping pay zones, this information gap between the bit and the tool could be critical. For this reason, systems have been developed that allow measurements to actually be taken within a few feet of the bit. Although LWD tools work in generally the same manner as conventional logging tools, keep in mind that tool responses will most likely be different in highly deviated wells from what they would be in vertical wells, and that these responses require special methods of interpretation. The integration of real-time drilling measurements and well logging has opened up some powerful, even revolutionary avenues. Not that long ago, developing a detailed well profile would have been pretty much the end of the story as far as directional planning was concerned. The next step would have been to drill the well along this pre-assigned trajectory and make course corrections as necessary. We refer to this process as geometric steering. Geometric steering has served the industry well, and it remains an important aspect of directional drilling. With a bent housing positive displacement motor, a well-designed bottom hole assembly, and MWD capabilities, it's possible to minimize wellbore deviation and stay on course simply by changing the tool face orientation as needed. But as companies have begun drilling longer horizontal and extended reach wells, they found that simply staying on target may not be good enough once we reach the productive interval. The reservoirs that these wells aim for are often very thin and sometimes steeply dipping and heterogeneous. It's all too easy to follow a pre-assigned trajectory right out of the pay zone. A difference of even a few feet can result in an unsuccessful well. Fortunately, integrated MWD and LWD capabilities have given operators the alternative of geologically steering wells, of using real-time formation measurements to stay within target intervals. In a growing number of instances, operators have been able to geologically steer wells away from zone boundaries or fluid contacts and execute successful well completions. For example, in one case, MWD and LWD logs were used to steer a well into the target zone. Soon thereafter, the resistivity began to decline. This decline, together with the true vertical depth of the bit, indicated that the well course was returning to an overlying shale layer. With this information, the directional driller was able to take corrective action and correct the well course.
The benefits of improved directional software, steerable bottom hole assemblies, and real-time analysis have been most apparent in the area of horizontal drilling. In the next unit, we'll consider horizontal wells in more detail and look at some of the challenges involved in drilling them. Horizontal wells entered the mainstream of oil and gas operations during the 1980s, helped along by some major technological breakthroughs and dramatic initial successes. In a number of fields, they've significantly outperformed conventional wells in terms of increased productivity, improved ultimate recovery, and lower overall development costs. There have also been disappointments along the way, which have shown that the benefits of horizontal drilling are largely contingent upon reservoir characteristics.
Horizontal wells work to best advantage in relatively thin, laterally continuous formations with good vertical permeability and a tendency toward drawdown-sensitive problems such as water or gas coning. The reasons for this have to do with the relationships that define horizontal well deliverability. For a discussion of these relationships, you can refer to the module PE 307, Horizontal Wells, Completion and Evaluation. Drilling the types of formations that are conducive to horizontal wells requires a high degree of directional planning and control. Horizontal wells generally follow a build, hold, and build pattern, consisting of a vertical section, or in some cases an inclined section drilled with a slant rig, a bend section where the transition from vertical to horizontal occurs, and a horizontal section, which is drilled through the target zone.
From this basic well profile, we can classify a horizontal well according to its bend section's radius of curvature as long, medium, short, or ultra-short radius. The most critical issue in assigning a radius to a given well is to select the curvature that results in entering the target zone at the most favorable point.
A long radius well has at least one section where the build rate is less than 5 or 6 degrees per 100 feet, and the build radius is 1,000 feet or more. Long radius applications include drilling multiple extended reach wells from offshore platforms or other single surface locations, drilling exploratory wells over long intervals, and selective completions requiring zonal isolation. Long radius drilling can employ either a conventional rotary bottom hole assembly or a steerable motor system for the bend and horizontal sections. It's not uncommon to use conventional rotary assemblies for long radius drilling. With an appropriate computer-aided design and accurate information on drilling conditions, this practice can prove quite successful. Often, however, this information is not available, in which case it may be more economical to run a steerable system. Along with allowing for the use of conventional drilling tools, long radius drilling offers flexibility in several other areas. It places no restrictions on hole diameter, bit type, coring, or MWD capabilities. It leaves open various options with respect to completion, stimulation, and artificial lift. And compared to shorter radius wells, it presents minimal dogleg severity problems. Long radius drilling also has some limitations, including high torque and drag tendencies, and greater difficulty in hole cleaning. A limiting factor in designing a long radius well is the ability to rotate the pipe at the surface as the bit approaches total depth. There may also be constraints imposed by shallow pay zones, lease boundaries, or other restrictions. In a medium radius well, there is at least one section with a build rate angle ranging from about 6 to 20 degrees per 100 feet in a rotary mode, and up to 30 degrees per 100 feet in an oriented mode. The radius of curvature ranges from about 300 up to 1,000 feet. Hole diameters range from 4 3/4 inches up to as high as 12 1/4 inches. Medium radius wells are appropriate for areas that could benefit from horizontal drilling, but where long radius methods are either unnecessary or impractical, as would be the case when lease boundary restrictions limit the well course. Medium radius methods employ specially designed motors for bend sections and either rotary assemblies or steerable motor systems for lateral sections. Heavy wall drill pipe can be used for build rates of up to 15 degrees per 100 feet. Higher build rates require compressive service drill pipe. Compared with long radius drilling, a medium radius well can reach the lateral section at a shallower depth and with less departure from vertical. Torque and drag tendencies are also less. Relative disadvantages are the inability to build angle using rotary methods and the fact that the tighter radius places more stress on the drill string. Although there are no restrictions on bit type or coring capabilities, MWD applications are limited for hole diameters smaller than about 6 1/8 inches. The build rate angle on a short radius well may range from 1 to 3 degrees per foot. The radius of curvature may be 50 feet or less, with a hole size of between 4 3/4 inches and 6 1/2 inches. Short radius applications include infill drilling in depleted reservoirs, drilling shaly intervals or other trouble-prone formations, and drilling multiple drain holes from one vertical wellbore. They are also proving useful for enhanced oil recovery. Short radius wells are relatively inexpensive. They provide easy, precise entries to the horizontal sections and can reach lateral displacement at a minimum measured depth. This makes them particularly appropriate and sometimes necessary for shallow reservoirs. Disadvantages of short radius wells include special requirements for such drilling equipment as articulated tubulars, limits on hole size and reach, limited azimuth control, and an inability to run logging tools or casing. Coring abilities are limited, and diamond or PDC bits must be used when drilling with a short articulated motor. A special class of short radius wells is the ultra-short radius well, which effectively has no bend section. Ultra-short drilling methods employ jetting techniques and coiled tubing to eliminate angle build sections and are used in soft, unconsolidated formations to drill multiple drain holes from existing vertical wells. Ultra-short systems are capable of drilling very small diameters. One system developed by Bechtel can drill 2-inch diameter holes to lengths of 100 to 200 feet. It's clear that there's a great deal of variety among horizontal well configurations. Selection of a given profile and the decision to drill horizontally in the first place depends primarily on reservoir management issues, which in turn dictate well objectives and completion requirements. We also have to think about lease boundary constraints and such considerations as the condition of existing vertical wells from which we may want to branch out. The starting point in planning a horizontal well trajectory is to specify the entry depth into the reservoir and a minimum drain hole length inside the reservoir. Reaching the target involves 3 phases: vertically drilling to the kickoff point, directionally drilling to the pay zone, and horizontally drilling within the pay zone. In drilling the bend section, we may either build angle in stages from the kickoff point or build continuously. The 4 main types of build curves are single build, simple tangent, complex tangent, and ideal. Your manual contains equations for describing these curves. Once we complete the bend section, our goals are to stay within the productive interval and, in naturally fractured reservoirs, to intersect the fracture network. It's in this phase of drilling that MWD, LWD, and geosteering capabilities become indispensable.
As is true for any drilling program, horizontal well planning and profile selection are ultimately based on economics. And the key to optimizing drilling economics is to avoid hole problems. In addition to planning and executing the well trajectory, there are a number of other areas that are of special concern in horizontal and high-angle directional drilling.
Drill string design, for example, presents some unique challenges. In vertical wells, the basic rule is to keep the drill pipe in tension and transmit weight to the bit by using drill collars and heavy wall drill pipe in the bottom hole assembly. In horizontal wells, the rules are more complex. Transmitting bit weight through the lateral section requires drilling in compression. The weight stack section may be in the vertical portion of the well, with compressive service drill pipe run in the horizontal portion. In the bend section, the pipe has to be able to withstand bending stresses, and in some segments buckling forces, while it transmits weight to the bottom portion of the hole. Heavy wall drill pipe is often used in this section. Torque and drag considerations play a big part in the drill string design process, and become increasingly significant as the radius of curvature and length of the horizontal section increase. Torque and drag result from frictional forces due to gravity effects, normal forces resulting from the curvature of the drill string, and buckling tendencies. These forces increase with increasing hole inclination and may serve as limiting factors during drilling and casing operations. Factors that affect torque and drag limits include the length of the hole's direction and lateral portions, the drill string makeup, the coefficient of friction, the rig specifications, and the drilling method. Horizontal and high-angle holes also require special considerations with respect to the drilling fluid program. One of a drilling fluid's key functions is to remove cuttings and clean the borehole. Problems that may result from insufficient hole cleaning include stuck pipe, premature bit wear, reduced penetration rates, formation fracturing and lost circulation, and high torque and drag. In a vertical well, effective hole cleaning takes place when the mud's average annular velocity, which tends to move cuttings upward, exceeds the average slip velocity, which tends to drag them downward. By contrast, in a horizontal hole section, annular velocity acts perpendicular to the slip velocity, and so does not act to counteract particle slippage. The mud has to move cuttings along fast enough that they can't accumulate as they drop out of the flow stream and form a cuttings bed. The annular mud velocity for effectively cleaning a highly deviated well is generally higher than that required for a vertical well. Borehole instability is another potential problem, particularly in the bend section of the hole. This requires careful attention to the mud weight and to the interactivity of the mud components with the minerals in the formation. Formation damage is an area of concern that's magnified in horizontal wells because they expose more of the formation than do vertical wells. Special attention to this aspect of drilling fluid design is, therefore, critical.
There are other drilling parameters that we haven't touched upon here. Our goal in this discussion has been to promote an awareness of the issues we have to consider in planning horizontal and high-angle wells as a basis for further study on this subject. Your manual expands on the basic concepts we've introduced here and contains a list of related references.